Okay, so this is another video on vectors and some more properties of them. As far as it goes so far, we have a vector, we'll just say v is equal to the vector 1, 2. We know we can add vectors together. If I have another vector w equal to 3, 5, well sure, I can add them together, I just add component-wise, add the x values, add the y values. And I know I can subtract them, just subtract the x values, subtract the y values, pretty straightforward. We know we can do scalar multiplication. If I have 5b, well that's just 5 times 1, 2, and I just distribute the 5 in, and I get the vector 5, 10. And essentially, I take my original vector and I make it longer. And in the last set of videos, we talked about unit vectors, and we did some applications, and we talked about taking a vector, say this vector right here, and writing it as a linear combination, where we could say v is equal to 1i plus 2j, or this would be w is equal to 3i plus 5j. And we kind of did several different vector definitions and basic operations on vectors. There's 2 more things we really want to go over. Your book has more topics, but we're just going to focus on these 2. And we have addition, subtraction, and multiplication, but so far we only have scalar multiplication like we just did there. Taking a number and multiplying it by a vector, which just gives me a vector that I stretch out or shorten based on what I multiply by. Now we want to do the dot product, which is where we take 2 vectors, say v is equal to the vector 1, 2, and w is equal to the vector 3, 5. I want to find their dot product. And by definition, the dot product, v dot w, you multiply component-wise and then add. So you do 1 times 3 plus 2 times 5. 1 times 3 is 3, 2 times 5 is 10, so that's 13. And the point here is, before we multiplied a vector by a scalar and we got a vector out. Now we multiply 2 vectors together and we get a scalar out. And the actual definition written in your book is, if v is equal to the vector a1, b1, and w is equal to the vector a2, b2, then v dot w is a1, a2 plus b1, b2. So it's nice and straightforward. Multiply component-wise and then add. The best thing is, you can expand this to different dimensions. So if we had 3-dimensional vectors, it would just be a1, a2 plus b1, b2 plus c1, c2. So it's a nice simple definition. And, well, there's actually some properties that come out of this. For the sake of argument, suppose we let v be the vector 1, 1. And we'll let w be the vector negative 2, 2. Well, what's their dot product? V times w is equal to, let's see, 1 times negative 2 plus 1 times 2, positive 2. Negative 2 plus 2 is 0. So apparently sometimes I can actually get a dot product of 0. But that actually does tell me something important. If we say, want to look at these vectors graphically, because it helps to look at them graphically and algebraically, well, let's see. My first vector, v, is 1, 1, which is right here. And then my second vector is the vector negative 2, positive 2, which is like right here. That's not exactly perfect. Let's see. More like right over here, maybe. There we go. And now apparently the dot product of those 2 turns out to be 0. But if we look at these things graphically, well, that actually forms the right angle. If you remember tangent, if this is 1, 1, you can do tan inverse of this triangle, and that will be 45 degrees. If you do the tan inverse of that, this will be 45 degrees, which means that has to be a right angle. And then the question is, well, if I multiply 2 vectors together, and in this case I got 0, and it turns out graphically they end up being perpendicular to each other, is that always the case? If you have two vectors that happen to be perpendicular like this, will their dot product be 0? If that's true, then it's actually helpful, because then, given any random vectors that we have that we just make up, if you want to know if they're perpendicular, you don't have to graph them and then try to see if you can somehow get the angle and use a protractor and see if the angle is exactly 90 degrees. If this is true, then you could just look at the dot product. Straightforward, direct. Dot product is 0, and they're perpendicular. But the question is that actually true? There is a formula for determining the angle between vectors, something like this. As far as the proof of it goes, it's in your book. I actually think it's interesting. If you want to see me write out the proof and explain it maybe in greater detail than your book, then send me an email and I'll make a video of it. But it takes like 5-10 minutes just to write the whole thing out graphically and algebraically, so I'm not going to do it on this video. And because, well, all things being equal, you don't actually need the formula in your book, as long as you understand what you're doing. And what I mean is, well, suppose in general, we want to find the angle between two vectors. So say we have two vectors. V is equal to 1, 1, and W is equal to 1, negative 3. So if I draw those, well, let's see. V is 1, 1, right here. And W is 1, negative 3, right here. I want to find the angle between them, which is this angle right there. Is there a way to do it? Like I said, there's a formula in your book, which works fine, but, well, maybe we can do it with just a trig we know. We know, and we'll keep everything color-coded to see if this will make it easier to see. I can actually find this angle right here, because I can just draw a triangle. That's the point 1, 1, so this is 1, that's 1. And I can actually find that angle right there. You should all know the formula by now. It's just tan inverse of 1 over 1, which is tan inverse of 1, which is 45 degrees. Which means that's a 45-degree angle right there. But then I can actually do the exact same thing on this triangle right here. This is still 1. This now is negative 3. So if I want to find this angle, I can do the same thing. Tan inverse of the opposite, which is negative 3 over 1, is equal to tan inverse of negative 3. Now we pull out the trusty calculator, and we get tan inverse of negative 3 is negative 71.6, which means this angle is negative 71.6 degrees, which just means, since I just care about the angle itself, that's a 71.6 degree angle. And now, can I actually find the angle between those vectors? Sure, just add these together. You would get 5 and 1 is 6, 4 and 7 is 11, 116.6 degrees, and you're done. And the reason I say that is, there is a formula for this. It's in your book, and I will write it out at the end of this. But all things being equal, as long as you remember the tan inverse trick in drawing a right triangle, you can find any angle for any vector on the plane, and then you can algebraically manipulate to get whatever angle you're looking for. Meaning, here I deliberately set this up, so all we had to do is add this angle and this angle. But suppose we have different vectors. Suppose we have, let's see, V is equal to the vector 3, 5, and W is equal to the vector negative 2, 4. So now if I draw them, let's see, 3, 5. So we'll say 3, 5 is like right here. And negative 2, 4 is like maybe right here. Now I want to find the angle between them, which is this angle right here. Now I can't just do my adding trick where I added this angle to get the angle between them. But if you think about it again, we'll do our best to color code everything here. Well, if I do my tan inverse trick, tan inverse will get me this angle using that triangle. And then tan inverse will get me this angle using that triangle. And then, since that's a straight line, that has to be 180. So I can just add those two together and subtract from 180. Doing it really quickly, let's see, we'll do this one since I have the purple marker out. Tan inverse of, let's see, in this case, it's negative 2, 4. So that's 4 over negative 2. So that's tan inverse of negative 2, which is 63.4 degrees. So this is 63.4 degrees. And then over here, if we do the same thing, we'll get tan inverse of 5 over 3. (59 degrees), which means this is 59 degrees. Now I want to find the angle between them. Well, let's see. I can just add these two together and subtract from 180. So 59 plus 63.4 is 122. And if I subtract, I get 57.6. So apparently this angle is 57.6 degrees. And there we go. And again, the point of this is there's a formula in your book. You can memorize a formula in your book. It looks a little bit weird, but you can memorize it and use it. But all things being equal, you don't really need it. As long as you can just draw these things in the plane and use tan inverse and a triangle. As far as the formula goes, just to see it and to see one use for it, the actual formula says cosine theta equals V times W over magnitude V, magnitude W. So essentially, in order to find the angle between two vectors, V and W, you take the dot product of V and W, which will be a scalar, and you divide by the product of the magnitudes of each vector. Again, the magnitudes will each be scalars. That's a scalar, so you'll end up getting a number. Then take the cosine inverse to get the theta you want. It's a little bit bizarre formula, but you can use it. If you want to practice with it, I would suggest, since we just did several problems, go back, use the vectors V and W that we did, plug them into the formula, and see what you get. The one thing I would stress is, this formula works using the angles from the horizontal. Meaning, the vector we just did over here was negative 2, 4. And when we drew our triangle, we used the reference angle and found the reference angle here. This formula uses angles from the horizontal, which means you have to use that right there. So just be aware of that. Okay? But